Okay, we're back, and we'd like to examine these four different scenarios. And in particular, we want to characterize each one of them as either being elastic collision, inelastic collisions, or maybe not a collision at all. So one thing we have to recall is the definition of these terms here is, first of all, elastic collisions are ones for which the kinetic energy throughout a process doesn't change or changes very little. So the kinetic energy is constant for elastic collisions. Inelastic collisions are ones where a significant portion of the energy changes or kinetic energy changes. And finally, maybe we won't be able to categorize some of these as collisions at all. So let's look at the first example. So the two billiard balls colliding. So normally when we think of two billiard balls colliding, from our own personal experience, we do have a sense that they tend to recoil and somehow maintain the same amount of kinetic energy that they had prior to the collision. And that we can generally take to be true. So two billiard balls colliding we can categorize as an elastic collision. Let's look at number two, a satellite slingshot around a planet. Well, on first glance, it might not seem that this is a collision because we are not really used to seeing objects so distant apart as being categorized as an actual collision. So technically, this is a collision. And one way to think about it is that we can consider what the satellite is doing far away from the planet as it approaches the planet, and then what it's doing far away from the planet after it leaves its interaction with the planet. So a more apt description here is that there's an interaction going on. And we can say that an interaction takes place in an area, in a region where the satellite is in close enough proximity to the planet so that it has actually increased its speed, let's say considerably. And so as it approaches, its speed increases. As it slingshots around the planet, its speed then starts to decrease. So whatever it gained in kinetic energy as it was approaching the planet is then converted, or let's say that it's, for now, we'll simply say that it's lost that same kinetic energy as it flies off in a different direction. And this, of course, is rooted in the fact that the gravitational pull between the two objects is a conservative force. So the force acting on, the force of gravity acting on the satellite is a conservative force. So we can characterize two as a collision, and also it's elastic. So the kinetic energy before the collision, and of course the system is the satellite, and the kinetic energy after the system, then we can consider to be close to equal. The third possible scenario is a car crash. So of course, a car crash is considered a collision. And from our own experience or experience of others, that we know for a fact that speeds can be very large before the collision, and then afterwards maybe just a slight recoil by comparison to the initial kinetic energies. Then the final kinetic energy is very, very small. So there is a significant, substantial change in kinetic energy throughout this collision. And then we can certainly characterize a car crash as inelastic. The fourth scenario is an object exploding into three fragments. So if we think about this a little bit, it doesn't quite seem like a collision in the usual sense. But technically, it does qualify as a collision. And we do have several objects to begin with. And it turns out that they're all static and stationary. These are the three fragments of the whole object. And then that's the initial scenario. So the final scenario is where these objects are flying off, these fragments are flying off in many different directions at different speeds. And so clearly the explosion itself we can consider to be an inelastic collision. So finally, we can categorize all of them together, and then we see then that the answer would be D. So let's examine further kinetic energy in collisions. And here we want to just kind of highlight what we just discussed and show some images. So off to the left, we have two billiard balls colliding. And that, of course, is what we normally think of as a collision, where on the macroscopic scale, it seems like that there was a contact, direct contact between the two. And one thing we need to remember as a rule of thumb is that objects that do not deform, such as these two billiard balls during the collision, if that's the case, then we can clearly see then that the kinetic energy stays constant throughout this interaction. So whatever the initial speeds are, we can calculate the initial kinetic energy of the pair, and then right after the collision, they fly off in opposite directions, for example, possibly. And then we can recalculate the kinetic energy, the total kinetic energy, and then we'd find that those are very, very close to being equal. Another example of elastic collision is this picture off to the right, and this was the example that we just looked at. So we have a satellite coming in from some great distance away, and as it approaches the planet, it starts to speed up, and it gets slingshotted around the side of the planet, the backside, and flies off into some other direction. And so we can roughly say that the collision occurs within some region in which the kinetic energy of the satellite is increased appreciably as it approaches and then decreases very quickly. And the initial and final states of the satellite would be taken to be this faraway initial incoming velocity and the faraway final outgoing velocity. So both of these cases are examples of elastic collisions in which kinetic energy is constant throughout the collision. Then let's look at inelastic collisions. So a general rule of thumb is that if there's a major deformation of the objects involved, then typically that characterizes a change in kinetic energy throughout the process. And of course, this situation here represents such an example. Also, we can come over to the right here and then look at the example that we had on the previous slide. So sort of conveying that image of an object that explodes. And we can talk about the collision a little bit differently in that we didn't initially have fragments that were moving and then went off in different directions. But initially we had fragments that were static. So initially no kinetic energy. After the explosion, which is technically the collision, then the fragments go off in different directions at very, very high speeds. So there is a tremendous amount of kinetic energy released. So throughout that process between the initial state and the final state, there's a very large change in kinetic energy of the system. And so that is certainly an inelastic collision. So let's look a little closer at a particular example of two objects colliding. And we're given that we have two masses, m1 and m2, and we're also given some of these velocities. So here is the initial scenario on the left. m1 is moving upward with some velocity v1 initial. m2 is moving to the left with some velocity v2 initial. And then the final situation is this. So m2 is static, it's not moving. And m1 is the only object moving after the collision. So m1 is moving off in some diagonal direction like this. And we're given several values here of several quantities. We have v1 initial, the magnitude of that is 3 meters per second. v2 initial is 4 meters per second, and v1 final is 5 meters per second. And the question is, find the angle that v1 final, which is this vector here, find the angle that it makes with respect to the horizontal. So we're looking for this angle theta. And what we have to do first is decide on what the system is. So the system, of course, is just the two masses together. And then we'd like to set up a coordinate system, so coordinate axes or directions. The way we do this, of course, is to make the problem as easy as possible to solve. And we can think about this particular initial condition, and it seems to indicate that it would be convenient to choose the up direction to be something that we normally consider up. Now, often we get used to calling that the y direction. And then the horizontal direction, we'll let that be x. And so this particular choice of a coordinate system matches nicely with the geometry of the initial state of the system. So what we do is impose as an equation, mathematically, that the total change in the system's momentum is zero. So between the initial state and the final state, total momentum is constant throughout. And then we sort of elaborate on this, and it is really the statement that the initial total momentum of the system is equal to the final momentum of the system. Now, of course, we have a vector equation here. So whenever we have a vector equation, that means that we have to equate like parts on both sides of the equation. In other words, like components. So let's look at the x components first. So the x components on either side of the equation are the initial x momentum and the final x momentum. And then by examining the diagrams, we can sort of elaborate on these. So momentum initial in the x direction, clearly m1 is not contributing to that because it's moving purely in the y direction, upward. But m2 is moving off to the left. And so we know that's going to be the negative x direction according to our choice in coordinate system. And so we end up with a minus, and then the momentum of m2 is simply its mass times the magnitude of its velocity. And then we look over to the final situation, and we want to elaborate on this a little bit and look at the x component of the total momentum of this. Well, clearly m2 doesn't contribute at all because it's stationary. And so m1, the fact that it's moving off in this diagonal direction, it has some motion in the x direction, or more precisely in the negative x direction. And to find that component, we can go ahead and think of this as a right triangle. And this V1 final, the magnitude of it as the hypotenuse of that right triangle. And so that tells us that the momentum in the x direction will be the mass m1 times the magnitude of V1 final. That would be P, and that times the cosine of this angle would give us this horizontal component. Now, of course, we have to realize that because theta is less than 90 degrees, that would give us a positive cosine. And so we just have to make sure that we're aware that the mathematics has to reflect the fact that this is moving, m1 is moving effectively in the negative x direction. So we tack on a minus sign to that. So for the y direction, we do similar type of analysis. P initial in the y direction must equal P final in the y direction. And then we unpack that. So P initial in the y direction will be m1 times v1 initial. So we come back to the initial picture, and we think about which one is moving, which one really contributes to y motion, motion in the y direction. Well, m2 certainly doesn't, but m1 definitely does. And we can see that because it's moving purely in the y direction, then its momentum contribution is going to be m1 times v1 initial. And finally, the final scenario is this. And then we want the other component of M1's motion. So precisely, that's going to be M1 times the magnitude of V1 final, which is this. But that's essentially the hypotenuse of this right triangle in terms of a geometric interpretation. And so what we're really looking for is the vertical component, or really the opposite to this angle here, the opposite side of the right triangle. So that's going to be M1 V1 final times sine of that angle theta. And then we want to check to make sure the sign is correct. We have essentially a plus there. And that makes sense because M1 is effectively moving in the positive y direction. So we have two equations here. And one thing we do have to remember is that it states that the two masses are equal. So that's going to simplify our problem considerably. And then what we can do then is just go ahead and set M1 equal to M2 and just call that something different without a subscript. Once we plug that into both equations, then the masses will cancel in both of them. So we divide through by m on both sides of both equations. And then also this left equation, clearly if there's a minus on one side and minus on the other, we could think about multiplying it through by a -1 and making those both plus, if we like. So finally, we end up with two equations for theta. This first equation involves an inverse cosine, simply because we had a cosine here. And to invert that, we use some trigonometry by taking the inverse cosine of both sides of the equation, and of course dividing both sides first by V1 final. And so we get theta equal to the inverse cosine of some ratio between two velocity quantities, really in particular V2 initial over V1 final. This equation, on the other hand, gives us something similar, but now it's an inverse sine of V1 initial over V1 final. And at the end, we can find our answer by introducing the actual numerical values for these velocities and then just performing the calculation to find theta. So let's look at this problem. So it's really the same problem. So the two colliding objects, exactly the same numbers. And now the question's different. What we want to know is the collision elastic? So we have to recall what that means and the fact that it involves kinetic energy analysis versus momentum analysis. So take a moment and think this one over, and then we'll come right back and solve it.